The first law of thermodynamics is essential for understanding thermodynamics and for understanding the world. The first law can be used to calculate how much heat is transferred to or from a system, how much work is done on the system, or how much work the system actually does. The first law says that the change in internal energy of the system is equal to the work added to the system plus the work done on the system. And so that's the best definition for the first law. Now, if you assume the universe is actually a closed system, then you can actually interpret the first law to mean that energy is conserved as long as you neglect nuclear reactions where matter can be converted into energy and energy into matter. And so with this movie, you should be able to describe how energy is converted from one form to another form, and yet is conserved. Describe how the universe can be separated into a system plus its surroundings. This is a very important picture for thermodynamics. You should be able to calculate the change in internal energy of a system from the amount of heat added to a system and the amount of work done on a system. You should be able to describe what state functions are and what path functions are. You should be able to describe what it means for internal energy, why it's important that internal energy is a state function, and heat and work are path functions. And so energy is the capacity to do work or transfer heat. Some forms of energy include heat, light, electrical, kinetic, and potential. And so by the diver climbing the platform, he's increasing his potential energy. Potential energy is just energy of a motionless body by virtue of its position. The higher the platform, the higher its potential energy, the less stable. There's also chemical potential energy, which is an analogous form of energy. Now, but when the diver jumps, he's converting his potential energy into kinetic energy. If we neglect wind resistance, his kinetic energy when he hits the water should be exactly equal to the difference in potential energy from the top of the platform to the water. Kinetic energy is the energy of motion. It's equal to 1/2 mv squared, where m is mass and v is velocity squared. And so if we think about a boulder rolling down a hill, initially the boulder has high potential energy, and that potential energy is being converted into kinetic energy. The amount of kinetic energy produced is exactly equal to the difference in potential energy of the boulder from being on top of the hill to at the bottom of the hill. Some other ways we can transform energy: we can think about chemical potential energy into heat, so combustion of a fuel. Heat to chemical potential energy, if we're converting a liquid to a gas. Chemical potential energy to electrical energy. Talk about batteries, electrical energy into chemical potential energy. So you can think about electrolysis of water or charging a rechargeable battery. And so in all cases, we're converting from one form to another form.
A buffered luminol solution with a copper 2 catalyst is added to the funnel on the left. A hydrogen peroxide solution is added to the funnel on the right. On releasing the rubber tubing, the solutions mix. The chemical reaction generates energy which is seen as blue light. This process is chemiluminescence. When the reacting solution mixes with a dye, fluorescein, the light energy from the reaction causes the fluorescein to give off a greenish light in a process called fluorescence.
And so a kind of cool reaction, and what we're seeing is a transformation from chemical potential energy into light energy. Again, energy itself was being conserved, just changed from one form to another form.
Potassium chlorate is sprinkled on a small mound of red phosphorus. A gentle tap with a hammer causes the mixture to explode.
And so another cool reaction, again, we're seeing chemical potential energy, but this time being transferred into heat and light.
In this experiment, we are looking at the explosive decomposition of a compound of nitrogen triiodide. This brown compound is so sensitive when dry that just touching it with a feather causes an explosive decomposition. It forms nitrogen and iodine. Like this mousetrap, which releases potential energy from the spring, the nitrogen triiodide releases chemical energy. When it decomposes into its elements, nitrogen and iodine.
When nitrogen triiodide, the dark-colored solid, is dry, it is very sensitive to touch or any vibration. Simply touching it with a feather causes it to explode or detonate. One detonation causes another to occur. One product of the reaction is violet iodine vapor.
And so the nitrogen triiodide has very high potential energy. The higher the potential energy, the less stable. Fuels have high potential energy. And so in this reaction, what we see is chemical potential energy is being converted to kinetic energy of the particles. And so the amount of energy released by explosion is exactly equal to the difference in chemical potential energy of the products and the reactants. Energy is being conserved. Now, an important picture in thermodynamics is this one where we think about the universe as composed of a system plus the surroundings. And so the only thing that will be transferred between the system and surroundings is heat and work. That's very important to remember, is that in this picture, the only thing transferred between the system and surrounding is heat and work. Now, the system you can imagine as being composed of a beaker. The surroundings is everything else. Now, the first law of thermodynamics, the change in internal energy equals Q plus W. So we can actually write the first law in terms of a equation. And so delta is change, U is internal energy, Q is heat transferred to the system. It's important to remember Q is positive when heat's going to the system, Q is negative when heat's going from the system to the surroundings. W is work done on the system. It's positive when work is done on the system, when work is increasing the internal energy of the system. And so if we have 5 joules of work done on the system and 3 joules of heat is emitted by the system, what is the change in relative energy of the system? And so we have to convert these words into numbers, into understanding. And so 5 joules of work is done on the system, so that means W is plus 5. 3 joules of heat is emitted by the system, and so it's going from the system to the surroundings, and so that would be a minus 3. And so our change in internal energy is going to be a plus 2. We can look at a chemical example. And so in this case, the bag is going to be our system. We're going to put some solid carbon dioxide inside.
Solid carbon dioxide vaporizes in an endothermic process as it absorbs energy as heat from its surroundings. If the CO2 is in a sealed non-rigid container, such as a plastic bag, the absorbed energy performs 2 functions. It vaporizes the solid and provides the energy for the expanding gas to perform work by moving objects such as a book or the molecules of the surrounding atmosphere.
And so we went from a solid to a gas, and so heat had to go from the surroundings to the system. And so in this movie, Q was positive. Again, our system is that bag. Now the bag actually lifted the book, so the bag, our system, did work, and so in this case, W was actually negative. And so internal energy is a state function, meaning that the change in internal energy only depends on the final initial state. That's fairly important. Work and heat are not state functions. And so heat and work actually depend on the path. Now, some types of work include expansion, weightlifting, electrical. We're only going to worry about expansion. And so for expansion work, W, the amount of work done on the system, is equal to minus P delta V.
A gas confined, such as the gas in this cylinder, exerts a pressure on the surfaces that confine it. Pressure is a measure of the force exerted on a unit area. The pressure confining the gas in the cylinder is measured by the force on the piston per unit area. When a gas expands, it does work against the surroundings. In this case, the gas does work by lifting the piston. The work done is given by the force exerted times the distance over which the force operates. In the expansion of the gas, the force is exerted over the distance shown as delta H. The work done is given by the product of the volume change times the pressure. The pressure might be kept constant in such an expansion by heating the gas continuously as it expands. If the pressure is not constant, the formula is still correct, but pressure must be evaluated at each stage of the expansion.
And so work done on a system is minus P delta V, where P is your external pressure, delta V is the change in volume. And so if delta V is positive, that means there's expansion. That means the system is doing work, and so work would be negative. If delta V is negative, you have compression. That means work is being done on the system. And so the negative in your delta V would cancel with the negative in front of the P, and that would give you positive work. Now, it's actually, here we have same initial and final states. And so one question you can ask is, does it matter how much work is done on the weight. And so if we put a big weight on it or a little weight on it, does it really matter? Now, because our equation is W equals minus P delta V, the weight is equal to the external pressure. The bigger the weight, the bigger the P, the more work. And so actually the weight does matter. Now, the amount of work done on the system or by the system is actually equal to the shaded boxes. In this case, it's work done on the system because we're looking at compression. And so notice that the bigger the weight, the bigger the shaded box, the bigger the work. Now, these are all isothermal processes. The internal energy of an ideal gas depends only on temperature. And so for an isothermal process, delta U is equal to 0. And so you can ask the question, where did the work go? And so if delta U is equal to 0, that means W equals minus Q. And so the extra work from the bigger weight actually goes into heat, going from the system to the surroundings, because this is an isothermal process. And so the bigger weight actually corresponds to a less efficient process. More heat was transferred from the system to the surroundings. And so larger the weight, the faster the piston moved, the more kinetic energy is transferred to the gas particles, the higher the temperature, the more heat that actually had to be transferred from the surroundings, from the system to the surroundings to keep the system isothermal. Now, if we could just add a little bit more pressure than the internal pressure at each step, that should lead to the most efficient compression, the least amount of work. And so if the external pressure was infinitesimally is bigger by an infinitesimal amount than internal pressure, that would lead to the most efficient process. And if we did that slowly, this was actually referred to as a reversible process. It's an idealized limit. And so the reversible process is the most efficient. Again, remember that the shaded region, the colored region, is actually equal to the work. Now in this case, our external pressure is actually not constant, and so we have to do an integral. So work is equal to minus the integral of P dV. Now, if we assume we're talking about ideal gas and it's isothermal, P equals nRT over V, we can plug in nRT over V for P in the integral. And so we get work is equals minus nRT times the integral of 1 over V dV. And we can take the nRT out of the integral because they're constant. Again, this is isothermal, so T is constant. And the integral of 1 over V dV is equal to natural log of V. Natural log of V2 minus natural log of V1 is equal to natural log of V2 over V1. And so we get for reversal isothermal compression, work is equals minus nRT natural log V2 over V1. But again, reversal process is the most efficient way of doing work. It is also equal to the maximum amount of work that a piston can do. Now here we have initial point P2 V2 T1, final point P1 V1 T1, and we can actually imagine 3 different paths going from the initial point to the final point. And it's kind of interesting, in all 3 paths, delta U has to be constant because again, U is the internal energy is a state function. But we can actually see how Q and W changes by using the different paths. And so for path A, it's isothermal, meaning constant temperature and reversible. And we saw for that case, and again, work is being done on the system because we're compressing it. V2 is bigger than V1. Now, change in internal energy, because we're talking about isothermal, ideal gas, change in internal energy is 0. Where we calculated the work done for a reversible isothermal process is just equal to minus nRT natural log V2 over V1. Again, Q is going to be plus nRT natural log V2 over V1. Now, if we look at the second path, going past C plus B, now for path B, it's adiabatic, no heat transfer, Q is 0, so delta U is just equal to W. To calculate U, where temperature goes from T1 to T2, du dt is equal to CV, which is the heat capacity constant volume. And so multiplied by dt, we get du is equal to CV dt. Take the integral, and that gives us W. Path C, V is constant, so there's no work, and so delta U is equal to Q. And so we can calculate Q, again, very similar to what we calculated W. For the entire process, we get that delta U is equal to that, which again is equal to 0. Now for path D and E, W is equal to minus P delta V. Now for E, V is constant, and so there is no work. For D, pressure is constant, and so we can just use minus P delta V. For the entire process, this is what we get. Now this is kind of cool, and here's our three paths. And so again, we see delta U is 0 for all three of them. It's a state function, does not depend on the path. And we see Q and W actually change depending on what path we're talking about, their path functions. This is a really nice illustration of the difference between a state function and a path function.